welcome to Homeschool. Hope everybody are doing good. And I am with class 11 chemistry. The chapter is hydrocarbons. Hydrocarbons is one of the most important chapters in case of organic chemistry. In my previous videos, I discussed every aspects of basic organic chemistry, isn't it? We discussed how to name organic compounds, different organic compounds having different functional groups, about their naming, about their classification, and we had seen very basic aspects of organic reactions. So how they react, what way they react, and what are the different electronic effects that we observe in organic compound, right? So everything we discussed in a detailed way. And coming to this chapter, this is just the continuation of organic chemistry, where you are going to study about the chemistry of the most important and basic organic compounds. So here we will try to understand how a class of alkanes can be prepared and how they react. Okay, so we know what was alkanes. We studied in the previous chapter. Alkanes are nothing but single bond containing organic compounds. They do not contain any functional group. You just observe carbon and hydrogen. So after all, that is what the definition of hydrocarbons, isn't it? So hydrocarbons are the organic compounds which have only carbon and hydrogen. You will not find any functional group, isn't it? So we are going to study the detailed aspects of such hydrocarbons. So what are the different hydrocarbons that you can observe? First variety is alkane. Second variety is alkenes, isn't it? So alkenes, you will observe double bonds between carbon atoms. And the third type of hydrocarbon is alkynes. So in case of alkynes, you will observe triple bond between carbon atoms, isn't it? And the fourth type of hydrocarbon, the most important variety, that is aromatic hydrocarbon. So about these organic compounds you are going to study in a chapter. So what do we study about them? We just study about the basic introduction. So we'll try to understand how these things can be reactive, whether they can be reactive or not. If reactive, what way they react, all of them. And then we will study about their nomenclature, and then certain aspects of isomerism. Then we will study the different methods of preparation, physical properties as well as chemical properties. So these are the various things we are going to study about each and every type of hydrocarbon. So today I am starting with the first variety of hydrocarbon, that is alkanes. So every type of a organic compound, we follow a particular pattern in our study, guys. So actually first thing we discuss about them is some general introduction, okay, and then we study something about the naming. Later, if they show any isomerism, special isomerisms, then we discuss about them. And later we will go for their preparations. So how can we prepare alkanes in a different way by different reactions? So all the preparation reactions, the preparation methods we will discuss in a detailed way. And later we will go for studying something called physical properties. See, under physical properties, we discuss very general aspects like boiling point, melting point, solubility, So all those things will come under physical properties. And finally, the most important part is chemical properties. So under chemical properties, we discuss how they react, with what type of compounds they react, and what type of products you get out of them, right? So it's like their uses. So what do we discuss in chemical properties? It's their uses. Uses here means the way they react, what are the different special reactions they undergo, which are the new organic compounds that you can prepare from these guys, all of them we will discuss under chemical properties. So every hydrocarbon is studied under these headings only. So first we'll discuss their introduction, then naming them, isomerism, preparation methods, physical properties and chemical properties. Okay, so in the entire organic chemistry chapters, both in 11th and 12th, every organic compound, type of organic compound is studied in this pattern itself, in these headings itself. Okay, so you must carefully understand the pattern, like in which way we are going to study these types of compounds. Okay, fine. So let us start with the first variety, alkanes. So what we have to discuss, the first thing is introduction. So today in this video, I am going to complete the introduction part, naming part and isomerism. Okay, and in my next video, I am going to complete the preparations of alkanes. Then in the third video, I am going to complete the physical properties as well as chemical properties of alkanes. Okay, so this is how about alkanes I will complete the concept in 3 different videos. Fine. So let's quickly go to the topic, the general introduction about alkanes. So we all know alkanes are nothing but, carbon-carbon single bond having hydrocarbons. So these are the hydrocarbons which have only carbon and hydrogen, and between carbon atoms you only have single bonds. Okay, so that is the first point to be remembered. And now the second point is every carbon in alkane is sp3 hybridized. Okay, so you must have an idea about this hybridization, guys. So about this hybridization we have discussed in my previous chapter, right? So what way you can identify that which carbon has what hybridization, all of that we have discussed. So any carbon which has got single bonds around it, then that carbon will always show sp3 hybridization. Okay, so whenever you have sp3 hybridization, then the bonds around such carbon is always arranged in a tetrahedral fashion, isn't it? So bonds, the 4 bonds which are there around every carbon is always there in what shape? It is there in a tetrahedron shape, right? Okay, so all of that we already know. Fine. And one major thing is these alkanes are also called with the name paraffins. So what do you mean by paraffin? Paraffin in the sense little affinity. So they are the organic compounds which show little affinity. Affinity in the sense attraction. Okay, affinity is nothing but they are very, very less reactive. So what do you mean by this word? These alkanes are actually inert. I can say inert or less reactive with other substances. Okay, so they are actually inert at room temperature. So at room temperature, these alkanes do not react with acids, they do not react with bases, and they do not react with any substances. That is why they are called with the name paraffins. So it's a Greek word. Para is nothing but little. Affins, affinity means what? Attraction. So they always show very, very little attraction towards other compounds. Okay, that means in a normal language, what we can say is they are not at all, they are very, very less reactive. They are inert at room temperature. Okay, so if you want to see their reactions, you can only observe at high temperatures. So at room temperature, they do not react with any chemical substance. So that is the reason we call alkanes as paraffins. Fine. And these alkanes will have a general formula CnH2n plus 2. So what do you mean by N here? N is nothing but number of carbon atoms. Number of carbon atoms. So whenever you have carbon atom 1, then what will be the formula of alkane? It will be CH4, right? So substitute 1 in N place. So what do you get? C1H. 2 into 1, 2 plus 2, 4. So the first member of alkane is CH4. What do we call its name? We call this alkane as methane. So we had seen all these in the nomenclature, right? So I'm not going into much details about the naming of alkanes because it is already covered in one of my video called nomenclature of hydrocarbons. Okay, saturated or aliphatic branched hydrocarbons. You know, there is a video. The link is provided in the description. You can go and check it out. So in this video, I'm not actually covering the naming part because as a whole, I have already completed, right? Okay, so just the few members, I will list it out here. So the first member of alkane is methane, which is the second member. How do you write the formula? It is C2H6, right? So how do you write its elaborate formula? CH3 bond CH3. So this is called with the name ethane. So whenever you have two carbon atoms, we have to use the word eth. Since carbons have all single bonds, we are using a suffix ane, right? So we call its name as ethane. So now the next member is CH3, CH2, CH3, isn't it? So this is called with the name propane, right? So like that it continues. CH3, CH2, CH2, CH3 is called with the name butane, right? Okay, so actually these are very simple and basic alkanes where you have only the straight chain. Okay, so you may have many number of carbon atoms in a chain and you may have complicated alkanes like a branched alkane also. So you just observe this alkane here, right? So it has heavy branches, isn't it? So this is one of the alkane with so many carbon atoms and with some branches, right? So it can have a huge branches or small branches, anything, about their naming, everything we have discussed in that video, right? Fine. So these are the different types of alkanes actually. I mean to say the alkane can be as simple as this and it can be as complicated as this also. So you have different alkanes with different carbon atoms and different chain lengths. Okay, so this is some general introduction about alkanes, and about the naming I'm not covering here, as I said. So straight away I will go for the next important topic, that is isomerism, right? So what actually we mean by isomers here? See, isomers are nothing but we are comparing between two compounds. Say this is one alkane, this is another alkane. So we are just finding out what is similar between them and what is difference between them. Okay, so studying this itself we will call it as isomerism. So I have one alkane, the other alkane. What is similar? What is difference? Right? So this is what we mean by isomerism. So let's quickly go for isomerism and what are the different isomerisms that you can study and observe in case of alkanes. Right? See students, here there are two types of isomers possible in case of alkanes. Actually in case of isomerism you have different types of isomerisms. So among so many isomerisms, two important types of isomers you will observe in case of alkanes. They are chain isomers. The first variety is chain isomers. And then second variety of isomerism, that is isomers that you observe here, is conformational isomers. Okay, so conformational isomers. So this is really very important. Okay, so let's discuss what do we mean by chain isomers. So as the name suggests, here the similar point between two alkane is molecular formula. Molecular formula will be similar, but the chain lengths are different. I told isomers are nothing but it's a comparison between two alkanes here. Okay, so what is similar here? Molecular formula is similar, but chain length, the structural formula is different. Okay, so let me write its definition now. The chain isomers are nothing but the two alkanes having same molecular formula but different chain lengths. Okay, different chain lengths. So such isomers are called as chain isomers. So let's talk about the chain isomers now. Fine. So suppose you have an alkane methane, right? So how many ways you can write this? There's only one carbon. So how many ways you can write its chain? Say the chain has only one carbon. There is only one way of writing the formula, right? There is only one way of writing a structure. So how do you write the structure here? Just the 4 hydrogens, you will show it around. So in this case, chain isomerism is not possible, right? So suppose you have 2 carbon containing alkane. So what is a 2 carbon containing alkane? CH3, CH3. So this is the only way of writing 2 carbon atoms. So writing this is similar to writing this. So anyway, so the chain, this is the only possible way of writing a chain. So even in this case, you will not observe chain isomerism. Coming to the third variety of alkane, that is propane, CH3, CH2, CH3, right? So how many ways can you introduce any branches here? So writing this is similar to writing this. So writing something like this is similar as writing this. So this is a chain, this is a chain. Both names are propane, right? So they cannot make isomers. What I told you, formula has to be same, chain length is different. Okay, so the structural formula has to be different. So in these 3 cases, chain isomerism is not possible. So if you want to observe chain isomerism, you should at least have 4 carbon atoms in a chain. 4 carbons in a chain you must have. Okay, so only then chain isomerism is observed. Okay, now let's go for 4 carbon atoms having alkane. Okay, to observe chain isomerism, that is C4H10. Okay, so how many ways this C4H10 can be written? So one is a straight chain compound, right? So one is this CH3, CH2, CH2, CH3. So what is its formula? C4H10. What is its name? We will call it as butane. It can be called as butane, right? So what is the other way of writing a structure for this formula? I can also write C4H10 as CH3, CH, CH3, CH3. See, one of the CH3 I have introduced as a branch in between, isn't it? So what is the formula here? How many carbon atoms? It is 4. How many hydrogen atoms? It is 10. You see, this compound has C4H10. This compound also has C4H10 formula, but both are entirely different. This is called as just butane or N-butane, whereas this is called with the name isobutane. So remember, anything you put as a branch, then we use the prefix iso in a common nomenclature. Okay, so butane has a different property, isobutane may show a different properties. Actually, both are different compounds. But what is similar between them? Similarity is molecular formula. What is difference between them? Difference is the way you write the structure. The chain lengths are different. Here you have a single linear chain, but this is a branched chain. Okay, so this is what we mean by chain isomerism. Remember, such chain isomerism is observed in alkanes, but it cannot be observed in 1 carbon, 2 carbon, 3 carbon containing alkanes. It cannot be seen. Whereas to observe this chain isomerism, our alkane must at least have 4 carbon atoms. Okay, so now questions will be asked like this. So how many possible chain isomers can be observed for C4H10? So how many isomers that you can observe? two, right? So two chain isomers you can observe. What are they? One is N-butane, the other one is isobutane, right? So if I ask you a question, how many isomers are possible for the alkane which has a formula C5H12, that is pentane? So pentane shows how many chain isomers. So how many ways you can write this pentane, right? How many different structures you can show this C5H12. So that's what you will have to try. So can you able to try? Just pause the video and try how many ways you can write C5H12, right? So the way we have written C4H10 can be written in only two possible ways. Can you think of any possible way of writing this? No. Only two possible chain isomers are formed in case of C4H10. Likewise, try writing chain isomers of C5H12. See guys, for C5H12, one way of writing is that linear one, CH3, CH2, 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 1, 2, 3, 4, fifth carbon, that is CH3. So this is called as N-pentane, right? So whenever carbon atoms are arranged in a single linear fashion, then we use this letter N. N means normal, okay? It's a normal chain. So N-pentane it is. So the other way of writing is I can introduce any branch here. See, CH3, CH, CH3, CH2, CH3. So if I ask you to write the IUPAC name, how do you write the IUPAC name here? It is, 1, 2, 3, 4, isn't it? So it is 2-methyl butane. 2-methyl butane is the IUPAC name. So this is another way of writing C5H10. See, even this guy has the formula H12, isn't it? So second isomer. Coming to the third isomer, how can I write C5H12? Highly branched structure, something like this. CH3, CH3, CH3. So what will be the IUPAC name of this compound? 1, 2, 3, right? So this can be 2, 2 dimethyl propane, isn't it? So, or in short, it can also be called as neopentane. So neopentane is a common name, but 2, 2 dimethyl pentane is the IUPAC name. Okay, so even this particular compound has a formula C5H12. So can you think of writing any other way for C5H12? Say if you write something like this, CH3, CH2, CH, CH3, CH3. Okay, will this be an isomer? Actually, this is similar to this only. If you try naming this, you will start numbering this way, right? So this is also 2-methyl butane only. So whenever the IUPAC names are matching, they are not the isomers. Actually, for the chain isomers, you will have different names. So when you had got different names, then they are isomers, chain isomers. When two compounds which have got a same name, in the sense they are similar, they are not the different compounds. So isomers are actually different compounds, but something is similar between them and something is different, right? So this is the way of checking whether it can become isomer or not. So any two structures which had got same name, in the sense they are not isomers. Okay, actually this and this is similar, so you cannot show this as the fourth isomer here. Okay, so there are only three possible. One is this, second one is this, third one is this. So C5H12 can show how many chain isomers? Only 3. Okay, so like that, can you all try for showing isomers for C6H14, C7 H16, C8H18, C9H20 and C10H22. So it's all trial and error. You will have to use your idea of drawing structures in various possible ways. Okay, see that the formula must match, names should be different, right? Say for C5H12 we had observed 3 chain isomers. For C4H10 we have observed 2 chain isomers. Like that for C6H14, can you tell me how many isomers are possible? right? So you can pause the video and try in your book that how many ways you can write the structures for for C6H14. Okay, so check with the structures and tell me how many chain isomers can be possible for C6H14, right? Fine. So anyway, I will give you one shortcut trick to remember. Okay. So the number of isomers possible for these guys. Usually for the competitive exam, they'll ask you for C7H16, how many chain isomers are possible? For C6H14, how many chain isomers are possible? So every time, you can't draw and check it out, right? Sometimes you may get confused and you will get messed up with the things. So it's better to remember something, okay, to give the answer in a best possible way. So this trick will definitely help you for any competitive exam, guys. So we have observed for C4H10 2 isomers, for C5H12 3 isomers are possible. Likewise for C6H14 5 chain isomers are possible. For C7H16 9 isomers are possible, and here 18, here 35, and here 75. Okay, so these are the magic numbers that you can remember. Okay, so I told you to put the structures for C6H14, no? So you will get 5 isomers. So try putting the structures in your book, right? So this is all about the chain isomerism. So for the chain isomers, what is similar? Molecular formula is similar for all the 3 structures, but the structures, the way you write the chain lengths are very much different. Okay, so hope you had got an idea about the chain isomerism. Now we will go for another important isomerism, that is conformational isomers. See guys, conformational isomerism is a very different isomers. You should visualize the things very, very carefully to understand this conformational isomers. See, it's very simple. Here the similarity is molecular formula and structure. Structure is also similar. Okay, so the 2 isomers which have similar molecular formula, similar structure, let me write the definition first. Isomers have same molecular formula and structure, but arrangement of atoms in space is different. So why do these atoms arrangement gets changed in a space time to time? It is because the CC bond which is there between the 2 carbon atoms can be rotated easily. That bond can be moved easily, it can be rotated. That's the reason, the atoms which are arranged in a space will change their position. Okay, so time to time. So those isomers are called with the name conformational isomers. So what we have to write here, the arrangement of atoms in space is different due to free rotation. This is very, very important, due to free rotation of carbon-carbon single bond. Okay, you should at least have one carbon-carbon single bond. So that carbon-carbon single bond can be rotated very, very easily. It has free rotation. Okay, so that's the reason the arrangement of atoms in a space will be different. I'll show you with one ball and stick model. So let us learn the conformations of ethane here. So conformations or conformational isomerism in ethane. Okay, because ethane is a very simple alkane. How do you write ethane? 2 carbons, right? Between them you have a single bond. This carbon has 3 hydrogens and this carbon also has 3 hydrogen. So I'll show ethane with the help of ball and stick model, guys. So to understand in a better way about conformational isomerism, I have got this ball and stick model. See, the black color balls are there, no? They are carbon atoms. So this carbon has 3 hydrogens. Even this carbon also has 3 hydrogens. Okay, fine. So this is your ethane. So initially you just check how these hydrogens are there in a space. They are there in a particular position, right? So now this bond is there, no? The bond between carbon and carbon can be freely rotated. See, it can rotate, it can freely move like this. So as I move the bond like this, the hydrogen atom's position is changed now. Previously it was in some position. See, now they are in some position. As I rotate, now the position of hydrogens in space is different, right? So as this bond gets rotated, the hydrogen atom's position gets changed in a space. So this is one isomer, this is another isomer, this is the third isomer. See, as I rotate, I get different isomers because the arrangement of atoms in a space is different, right? See, the structure is same, molecular formula same, just what is difference? Arrangement of atoms, that is particularly the hydrogen atoms in space, is getting different, right? So this is one isomer, I rotated, this is another isomer, again I rotated the bond, this is the third isomer, again I rotated, this is the fourth isomer, again I rotated, this is the fifth isomer. Like that, hundreds of conformational isomers are possible in case of alkane. Okay, so this is ethane. Here hundreds of isomers are actually possible, guys. So we don't have names for all those conformational isomers, but two conformational isomers are very important to study. We have given names for them. They are nothing but, staggered conformer and eclipsed conformer. Okay, so what do you mean by staggered and eclipsed conformer? That is what we are going to study. Okay, so you understood now what do you mean by conformers? So all these are, say this is one conformer, again rotated, second conformer, again rotated, third conformer. So as you keep on rotating, the arrangement of hydrogen atoms in a space gets different, right? So that is what we call conformers, or conformers are also called with the name rotamers. Okay, conformational isomers have another name, we can call them as rotamers also, isn't it? Okay, so now you just observe one thing, guys. Okay, you observe. See, I'm going to talk about staggered conformer and eclipsed conformer. So these staggered conformer is the most stable conformer, actually the most stable structure. Eclipsed conformer is least stable structure. So I can represent these structures in two different ways. First one is I can represent them. I can show it on a board, or we can write it on a paper in two different ways. Okay, so one is by Newman projection. One is by Newman projection formula. Okay, the other one is by Sahar's projection formula. We can draw their structures with the help of two formulas, guys. One was by Newman projection formula, by Sahar's projection formula. Okay, so there are two different ways of writing their formulas or structures. Fine. So what do you mean by Newman projection formula? How do we write staggered conformer and eclipsed conformer with the help of Newman projection formula? It's very simple. You just see, put a dot. This is like a front carbon, See, I am holding this ethane like this. So this is your front carbon and this is your back carbon. So the front carbon, I have shown it like a dot. The front carbon has, 3 hydrogens, right? Later we will put. And this is your back carbon. Okay, so this is front carbon, which I indicated like a dot, and the carbon which is behind, which you cannot see actually, it's behind, that we have represented as a circle. So the front carbon has 3 hydrogens, they are these, and the back carbon also has 3 hydrogens, right? So this is 1 hydrogen, this is 2nd hydrogen, and this is 3rd hydrogen. So this is what we call staggered conformer. So staggered conformer is written like this. Okay. So if you observe staggered conformer, the bonds of front carbon and the bonds of back carbon are actually far away with each other. So, such a conformer can be more stable, guys. So, if you can observe, this is what the staggered we say. Okay. So, these hydrogens and these hydrogens, there is nice gap. Actually, you see this white color ball and this white color ball, you see, actually nice gap is there between them. Okay. Got to know. So, enough distance is there between hydrogen atoms of front carbon and hydrogen atoms of backside carbon. So when you have this enough distance, repulsions will be minimum, right? Bonds, if two bonds are very near, bond is nothing but a pair of electrons. If two bonds are very near, you will observe lots of repulsions. But if the bonds are very far, if they are far away with each other, repulsions are minimum. No? Whenever repulsions are minimum, the compound gets more stability. So that is the reason we say staggered conformer is more stable. Okay. So this is how the staggered conformer looks, guys. Okay. So nice distance is there between hydrogen atoms of front carbon and back carbon. CH bonds have got nice distance. They stay far away with each other. So now as I rotate a bond, the staggered conformer will get disturbed. It becomes some other conformer. I'm again rotating. It has become some other conformer. I'm again rotating. It has become some other conformer. And now you see this. If you can look at this, okay, hope you can see this. If you can look at this, actually you don't have enough distance between this bond and this bond, right? They seems to be very near. So if the distance is reduced, if the bonds are very near, you will observe lots of repulsion, right? So more energy, less stable. So this conformer is called with the name eclipsed conformer. So how do we represent eclipsed conformer? Same. This is front carbon. This is back carbon. So these are the hydrogens of front carbon. Right, so these are the hydrogens of back carbon. You see, the hydrogens of front carbon and back carbon, the distance is very little, right? Like you observe here, you observe from your angle, you see the distance between this ball and this ball is very, very little, isn't it? So, if the distance is very little, I mean bond interactions are too high, the structure become less stable. Okay, so this conformer is called with the name eclipsed. Then remaining all conformers between staggered and eclipsed, lots of rotations are possible, right? Lots of conformers are possible, right? All of them collectively called with the name skew conformers. Skew conformers. So what do you mean by skew conformers? It is the conformers that come in between staggered and eclipsed. Staggered and eclipsed. Okay, say for example, this is what I said, this is eclipsed, isn't it? Because, because this bond and this bond is very near, this is eclipsed. And now, this is actually staggered. And automatically at a time, the structure will not be changed into staggered. See, this is eclipsed. Slowly, the bonds moving. Slowly, again this is another conformer, again this is another conformer. Now you see, now you got staggered. So after many conformers, you are getting staggered. And now as I rotate after many conformers, you will get eclipsed. So between staggered and eclipsed, there are many conformers, right? So they are all collectively called with the name skew conformers. Okay. So among hundreds of conformers, because many ways I can rotate the bond, many ways the bond can be freely moved. So as it moves, you get a different arrangements. They are called conformers, I said. So among hundreds of conformers, we are concentrating only two conformers. One is the most stable conformer, that is called as staggered. The other one is less stable conformer, that is called as eclipsed. Okay, so this is the way of representing staggered and eclipsed by Newman projection formula. Okay, and then by using Sahar's formula, it's different. Say this is one carbon, this is another carbon. So usually these are the hydrogens of this carbon and these are the hydrogens of this carbon. So actually this is the staggered conformer. I represented it with the help of Sahar's projection formula. Okay, and eclipsed, how do we represent that? This is the CC bond, this is one carbon, this is another carbon. H H. Okay, so H, see, hydrogen atoms are actually slightly near. Okay, so this is what we call eclipsed conformer, which I have shown with the help of Sahar's projection formula. Okay, so usually Newman projection formula is very important, and it is in this conformer you can clearly visualize that. You can say that yes, the hydrogens of front carbon and back carbon is far away, so that repulsions are minimum, so stability is more. And here you can clearly visualize the hydrogen atoms are very near, so stability is very less, repulsions are very much high. Okay, fine. And actually speaking, the CC bond free rotation is hindered by these bond repulsions, guys, and that bond repulsions are called with the special name called torsional strain. Torsional strain. So what do you mean by torsional strain? This is nothing but repulsions between the bond, repulsions between the bonds, okay, between the bonds that disturbs, okay, so that disturbs CC bond rotation, that can hinder the CC bond rotation, I can say. Okay, so in case of staggered conformer, torsional strain is very much minimum. In case of eclipsed, since the bonds are very near, repulsions are more, so CC bond rotation is also hindered to some extent. Okay, so we say torsional strain is very much high in eclipsed, torsional strain is very much low in case of staggered. Okay, so this is actually their stabilities. Relative stability always depends on so-called torsional strain. Okay, so this is all about staggered conformer and eclipsed conformers of ethane, guys. Okay, so this is one of the special isomerism you will observe in alkane. So why this isomerism is observed? It's all because of that CC bond is freely rotated. Okay, so that's why the arrangement of atoms in a space gets different. That leads to the formation of so many conformational isomers. Okay, so that's all about today's video. We have discussed the two important types of isomers in case of alkanes. In my next video, I will come up with the preparation methods of alkanes. So how can we prepare alkanes by different methods? All of them we will discuss. Okay, so till then, revise the concept and do subscribe our channel to learn the concepts in the easiest way. Thank you so much, guys. All the best.